We are Group 13. We are going to present our final project. Our topic is a text sentiment analysis system based on tweet content. Okay, our goal is to develop a robust model capable of accurately predicting the sentiment of text data is positive or negative. Specifically on tweets, sentiment analysis is a crucial tool in natural language processing, enabling business to understand customer opinions, monitor brand reputation, and make informed decisions based on public sentiment. Developing such a model presents several challenges. First, diverse language usage, including slang and idioms, complicated sentiment analysis. Secondly, detecting sarcasm and irony proves challenging for machine, demanding a deep understanding of language. Thirdly, multiple language text, which needs a more sophisticated model. Fourthly, contextual understanding is difficult because one word can hold multiple meanings depending on context. Last, handling OOV words, which is not presented in the dataset. Our primary goal is the same as mentioned in previous page, and our specific objectives include data processing, data augmentation, feature extraction, model training, model evaluation, and handling OOV words. We will talk about this objective later. Let's talk about the progress of our project. First, we are dealing with data processing because the original data is not complete. Second, data augmentation, which means enhancing our dataset. This augmentation instances are then combined with the original dataset to form an richful dataset. Third, feature extraction is about deriving features from the text data for numerical representation, which assigns score for negative, neutral, positive, and compound sentiment. And fourth, for module training, the dataset was divided into training and testing sets. Then a stacking ensemble model was built using logistic regression and random forest classifier as base model. Fifth, for module evaluation, the base model selected from grid search was saved. Various performance metrics were computed. Next step is to address OOV words. The text data were modified, replacing them with a special OOV token. And next, we are talking about related work to our project. The first is traditional machine learning method that require extensive feature engineering and struggle with context and OOV words. The second is deep learning model, LSTM. Its network capture text sequence but face challenges with OOV words and sarcasm detection. The third is transfer learning module and pre-trained embedding. Model like BERT and GPT-3 leverage large-scale pre-training on diverse corpora, enhancing sentiment analysis model with rich contextual information. The next is some data augmentation techniques, as mentioned before. The last material as referred is ensemble learning, combining models with techniques to improve performance. And our dataset is come from Kaggle. Its raw data contains about 55,000 tweets, and each tweet contains an identifier and a tweet text and a sentiment label. And we deal with the raw data as we mentioned before in the progress. And the platform we use to finish our project is Python with Jupyter Notebook. And these are some libraries we use in our project.
And the main approach. Data preprocessing is crucial for any machine learning project, including our sentiment analysis task. We begin by loading and cleaning the dataset, removing unnecessary columns and rows with missing values to ensure relevance. We standardize the text by converting it to lowercase, ensuring consistency. Regular expressions help remove unwanted characters, URLs, and mentions, stripping away noise and retaining the core content of the tweets. Additionally, we remove stop words like and, the, and is, reducing clutter and focusing on sentiment-bearing words. These pre-processing steps ensure our data was clean and standardized, laying a solid foundation for effective feature extracting and model building. To enhance our dataset and improve model generalization, we apply several data augmentation techniques. We use synonym replacement to introduce variability while maintaining meaning, helping the model recognize different expressions of the same sentiment. Random word deletions simulated incomplete text, ensuring the model could handle missing information. Lastly, word swappings created diverse sentence variations. These techniques collectively made our dataset more diverse and our model more robust. We use two main techniques for feature extraction: TF-IDF, vectorization, and sentiment features. TF-IDF transforms the text data into numerical features, highlighting significant words and reducing the weight of common words. Additionally, we use the VADER sentiment analysis tool to extract comprehensive sentiment scores, including negative, neutral, positive, and compound scores. By combining TF-IDF with VADER sentiment features, we provided our model with a rich set of features of accurately predict tweet sentiments. For model training, we use a stacking ensemble approach with logistic regression and random forest as base models. Logistic regression handles linear relationships, while random forest captures complex patterns. We combine these using logistic regression as the final estimator, improving robustness and accuracy. Research with cross-validation was used for hyperparameter tuning, ensuring optimal performance. This stacking ensemble technique allows us to build a robust model for accurately predicting tweet sentiments. In our project, handling out of OOV words is the managed implicitly through TF-IDF vectorization. TF-IDF assigns weights to words based on their importance in the training set. If a word in the test data is not in the training vocabulary, it is ignored in the TF-IDF featured space. This ensures the model focuses on known words, maintaining robustness and handling new or rare terms without needing a special token.
And now I will talk about our base model. For the base model of our sentiment analysis system, we utilize two key machine learning algorithms: logistic regression and random forest. For the first one, logistic regression, we get the C parameter into 10. The C parameter in logistic regression represents the inverse of regularization strength. It helps in balancing the trade-off between minimizing training error and generalizing well to unseen data, thus controlling overfitting. And the second algorithm, random forest, we get the max depth parameter to none. This parameter determines the maximum depth of each tree in the random forest. When set to none, the tree grows until all leaves are poor or contain fewer samples than required for splitting. Allowing unrestricted tree growth enables the model to capture detailed data patterns, potentially enhancing performance. However, this also increases the risk of overfitting, which is mitigated in random forest due to averaging the prediction from multiple trees. To optimize the hyperparameters of our models, we perform grid search with cross-validation. For logistic regression, we test C values of 0.1, 1, and 10. For random forest, we test unestimated values of 50 and 100, and max depth of value of none, 10, and 20. And this is the script we use for grid search. After the execution, grid search fit free falls for each 18 candidates, totaling 50 fits. This concludes the explanation of our base model and the parameter optimization process. For our baseline, we use a simple logistic regression model. We start with the basic data processes, including text cleaning and TF-IDF vectorization. We assess our model using several key metrics: accuracy, precision, recall and F1 score, and RRC AUC score. And for the most important part, we obtained a high score of 0.9572, indicating strong performance in distinguished distinction between classes. And this is the result matrix of our program.
The confusion matrix visually represents our sentiment analysis model's performance by comparing its prediction to the actual sentiment in the test dataset. The vertical axis shows the actual sentiment, and the horizontal axis shows the predicted sentiment. And we can see the figure on the next slide. And that is the information of the confusion matrix. The high TN and high TP values show that the model accurately predicts a large proportion of both negative and positive sentiments. Relatively low FP and FN values suggest that the model makes fewer mistakes. This confusion metric helps us understand the types of errors the model makes, providing insights into areas for further refinement to improve overall performance. And the receiver operating characteristic curve is a graphical representation that illustrates the diagnostic ability of our binary sentiment classifier. And the vertical axis represents the true positive rate or sensitivity. And the horizontal axis represents the false positive rate. The blue line on the graph shows the model's performance at different threshold levels. And the closer this curve follows the left-hand border and the top border of the ROC space, the more accurate the model is. And finally, the diagonal dotted line represents a random classifier that makes random guesses. This serves as a baseline for comparison. And the AUC is a single scalar value that summarizes the overall performance of the classifier. An AUC of 1 represents a perfect classifier, while an AUC of 0.5 indicates a worthless classifier. In our case, the AUC is 0.9572, indicating that our model has excellent discriminative ability between positive and negative sentiments. And the ROC curve demonstrates that our model performs very well, with a high AUC score of 0.9572, showing its strong capability to distinguish between positive and negative sentiment accurately.
I will be presenting our findings on experiments conducted to evaluate our model's performance. We began with baseline model, using a simple logistic regression to set a reference point. Next, we investigate the impact of data augmentation by comparing models trained with and without augmented data. We also explored different feature extraction methods, focusing on TF-IDF features alone versus combining them with sentiment scores. Lastly, we performed a model comparison to evaluate the performance of our staking ensemble model against individual-based model. Moving on the results and the analysis. The baseline performance shown that our reference model achieved an accuracy of approximately 80% by incorporating data augmentation. We noticed improvement in generalization ability, which lead to higher accuracy and F1 scores when evaluating features extraction effectiveness. Combining TF-IDF with sentiment scores provide a more comprehensive text representation, enhancing model performance. Finally, we ensemble model's superiority was evident as the staking ensemble model outperformed and the individual-based models by leveraging multiple classifier strengths. We used the confusion matrix to determine that our model correctly predict a higher number of both positive and negative sentiments, with a relatively few misclassification. Additionally, the ROC curve and the AUC score demonstrate the model's strong ability to distinguish between positive and negative sentiments. So here is our example results from our model. The developed sentiment analysis model has various practical applications. First, in customer feedback analysis, business can be used the model to analyze feedback from social media reviews and surveys to gain into customer satisfaction and areas for improvement. Second, for the social media monitoring, the model helps monitor public sentiment on specific topics, brands, or events. Finally, the market research through the model. The companies can understand public opinion and sentiment toward products and services. Despite the promising results, our model has some limitation. Firstly, it may struggle with detecting sarcasm and irony. Secondly, the model is primarily designed for English text and may not perform well on text that mix language or are in different languages. Finally, let's look at the performance of our baseline model. The LSTM model performed better in capturing the sequential characteristic of the text, providing more accurate sentiment classification results. However, it requires more computational resource and training time. So here's our conclusion. To conclude, we successfully developed a robust sentiment analysis model. Our model achieved high performance. These results demonstrate the model's excellent discriminative ability and high accuracy in predicting sentiment. Additionally, we made effective use of data augmentation techniques. This method enhanced data diversity, leading to better generalization. However, our model still face some limitations, including the context-specific language. So, despite this limitation, our model has practical applications, including analyzing customer feedbacks, monitoring social media sentiment, and so on. So here is our contribution. Thanks for your listening.